so bright online. All right, so this is on page 17. Position vectors A, B, and C are that. We want to show that they are collinear. What does collinear mean? What do you think, if you were just using your English skills, what do you think collinear might mean? Okay. They share lines. So we got A, B, and C. Do you think these are collinear? Do they look like they share lines? All of them? All three of them? Two of them do, but not all three of them. How about if I take that and put it over there? If they're all on the same line, that's what collinear means. So we want to show that they're all on the same line. Here's A, here's B, here's C. Mathematically, what has to be true if they are on the same line? That wouldn't be true if C was over here. What's that, sorry? They'd have to have the same slope. So if this had the same slope as that, mine close, that would work. Now when we look at these vectors are three-dimensional. So we've got a thing in 3 dimensions, and if you go back to your grade 10 math, you say, I know how to find the slope of something in 2 dimensions, but how would you describe the slope of something in 3 dimensions? We could probably develop some math to do that, but there's another way that we can show they're collinear as well. Does it make sense that if you go from A to B, which would be that vector, A to B, and then you go from B to C, that if that is exactly equal to A to C as far as lengths go, and remember, we put absolute value bars around something to show a length, that only happens if they are on the straight line. That the length of AB plus the length of BC can only be equal to the length of AC if they are on the same line. Do you remember how to find the length of 3-dimensional vectors? First of all, let's figure out what AB is. Because right now we have position vectors. There's some origin somewhere. And we know what the position vector for A is. We know what the position vector for B is. And we know what the position vector for C is in 3 dimensions. But how do I figure out what vector AB is? Okay, add these 2 position vectors, right? First of all, we'd have to go, does it make sense you'd have to go this way first? That would be negative whatever that position vector is. And then you'd go in the positive same direction as position vector B. So if we look at position vector A is 2, negative 1, 1. And we want to go in the negative direction of position vector A. And then we'd like to add position vector B, which is 3, 2, negative 1, which will give us AB, which is 1, 3, negative 2. B to C, same idea. If we go back to the origin from B, that'll be negative 3, 2, negative 1. because that's position vector B. And then we'd like to go to C, which will be plus, and vector C is 6, 11, negative 7. Giving us 3, 9, negative 6. And finally, vector AC. We already know that negative A was 2, negative 1, 1, and C was 6, 11, negative 7. So we get 4, 9, 8, 10, wait a minute, what is it? 12, and negative 1. So here I use the position vectors each time to figure out now what is vector AB, what is vector BC, and what is vector AC. Because we want to find out if the length of AB plus the length of BC is the same as the length of A to C. Another thing you can do to check if your vectors are right, just with our vector addition before, does it make sense that if I add AB plus BC, even if they're not collinear, if you go from A to B and then go from B to C, that should always equal A to C as far as vector addition works. And if we look at our answers from A to B and B to C here, 1 plus 3 is 4, 3 plus 9 is 12, and negative 2 plus negative 6 is negative 8. So it's another way I can check along the way to make sure that my position vector addition and stuff and my actual vectors are correct. Now to find the lengths of each of these, the length of AB, square root of A squared plus B squared plus C squared. The length of BC be the square root of the first one squared plus 9 squared plus a negative 6 squared. And A to C's length, right? See what we're doing? We're just taking whatever the x is plus whatever the y is plus whatever the z coordinate is and squaring them all. So we've got AB as the square root of 14. Square root of 126. 126 is 9 times 14. So we can write this as 3 root 14ths. And here, (16) 144 makes 160 plus 64, 224. Which is 16 times 14, so that'll be 4 root 14. Write a statement: since the length of AB plus the length of BC is equal to the length of AC A, B, and C are collinear. And yes, when you did these with 2 dimensions, you probably did slopes as an easier way because slopes were easier to figure out than lengths. But now that we're working in 3 dimensions, how would you describe the slope of a line in 3 dimensions? You'd have like rise and run and up and down. I don't know. I'm not sure how you would describe it. Maybe you would have a triple ratio. Rise, run. We need another R word. And then I guess the triple ratio could be a slope. I don't know. I'm just rambling. I should probably shut this off.